Meow. Section 16.9, the Doppler effect. This is something you've all heard at some point. The Doppler effect is the change in frequency or pitch of the sound detected by an observer because the sound source and the observer have different velocities with respect to the medium of the sound propagation. So for instance, if you've uh, had a fire engine that's making noise, right? Like it's putting its siren out there, you can hear that in all directions. The sound goes out and the condensations are shown as these circles, right? Where those are the sound going out. We can imagine it being a single pitch. The wavelength is the distance between those condensations. So if the truck is stationary, you just everywhere around you hear the same thing. You hear that siren. If that fire truck is moving, you start to hear a different thing depending on where you're standing. If you're standing behind the fire truck, then because it's moving away from you, the wavelength appears to be longer. Longer wavelength, based upon our basic equation that the speed of the wave is equal to the frequency times the wavelength. The speed of the wave is set just by the air. So if the wavelength goes up, that means the frequency needs to go down because it's a constant speed. So as the siren goes by, or even just a car drives by, you hear this, the frequency drops. Versus if you are in front of the fire truck as it's coming towards you, it's moving and it's catching up with those condensations. So they're getting closer together or compressed. In that case, the wavelength is getting smaller. So what happens to the frequency? It's going to go up. That's what you hear as it starts to approach, where it goes, right? That increase in frequency is the Doppler effect. And we can actually quantify it in physics. So we'll first look at a moving source, like this fire truck. So at rest, it produces this normal wavelength, lambda. If it's moving, then the wavelength is modified, and the modification is going to depend on how fast the truck is moving. So that's what this is trying to show, that it's the original wavelength minus the speed of the source times the time, the period of it, which we could instead make into frequency. And so the frequency that's observed by the stationary observer is equal to the speed of sound divided by this modified wavelength. So the modified wavelength, lambda minus bs period. Instead of working with wavelength and period, we're going to switch to frequency because we're talking about sound and we usually describe sound and frequency. So the lambda becomes the speed of sound divided by the frequency of the source, and then Vs is the speed of the source, right? So that's an important note here. Our basic V is the speed of sound versus the speed of the source. And the Vs is the speed of source. So if we then do some algebra, we can cancel out one of those V's, one of those speeds of sound, and we can solve for the frequency observed that is equal to the frequency of the source, what the fire truck, what a fireman or firewoman would detect, times 1 minus the speed of the source divided by the speed of sound. This is when the truck is moving towards the observer, right? It turns out if instead the source is moving away from the stationary observer, we switch from having a negative sign to a positive sign in the denominator. So that's a key detail here. If the source is moving toward, we have this negative sign down here. If it's moving away from, then we have a positive sign here. So these are important notes to include with these equations. so that you can keep them straight, because that's one of the most important parts with solving these problems. And we can see that in this next example. So example 10, the sound of a passing train. A high-speed train is traveling at a speed of 44.7 meters per second. That is fast. When the engineer sounds the 415 hertz warning horn, right? Boop, boop. The speed of sound is 343 meters per second. What are the frequency and wavelength of the sound as perceived by a person standing at the crossing when the train is A, approaching, B, leaving the crossing? So remember, we need to decide for approaching and crossing, or leaving the crossing, all that's going to change is the positive or negative sign. So remember, approaching is the negative sign, and leaving, moving away from, is the positive sign. Once we have that, we are in good shape, right? We already have our speed of sound, which is the v variable. We have the speed of the train, which is our source of sound, so that would be our vs. And then the 415 hertz, which frequency is that? Is that FO or FS? This is what is generating the noise. This is the source. So I'd call that FS. And then perceived by the person who is not at the source, that is the observer. So that is what we are trying to solve for. So now we can plug and chug. So we find that approaching is the minus case. We can plug in those numbers, and approaching, it's 477 hertz. If instead the train is leaving, we still plug in 415 hertz times 1 divided by 1 plus 44.7 divided by 343 meters per second. And the frequency is now 367 hertz. Notice this matches our common experience, right? Relative to the frequency of the source, 415, when it's approaching, the frequency is higher. When it's leaving, the frequency is lower. Right? So those are our two extremes there. If we then wanted to get the wavelength of the sound, we could go to our classic V is equal to frequency times the wavelength. And so then we could plug in, solve for the wavelength, and it would just be the speed of sound divided by the frequency that is observed. And that would work. Right, so this describes if the source is moving. But with the Doppler effect just occurs anytime the source or the observer is moving relative to the medium. So the other case we have is if we have a moving observer. So here's a case where the observer is moving toward a stationary source. The source is now not moving, but the person is. You'll still have a Doppler effect here. So as the observer moves towards, they encounter the crests more frequently, and the frequency goes up. I won't go through the derivation here, but the frequency observed is now the source frequency plus their speed divided by the speed of sound. So it's a slightly higher frequency. So this is our grand takeaway. Observer is moving towards the stationary source. We have this positive sign. If it is moving away from the stationary sources, the observer, is now a minus sign, because this is reducing the frequency as you're moving away from it. So this is something you could hear if you yourself drove by, say, a fire truck, but the fire truck is stationary. You're now moving. You could hear the frequency change. That as you're moving towards, you're going to hear a higher frequency. As you're moving away, you'll hear a lower frequency. And you could sum all four of these equations up into one massive equation if you want. So the most general case is that the observed frequency is equal to the source frequency times the quantity of 1 plus or minus the speed of the observer divided by the speed of sound divided by 1 minus plus the speed of the source divided by the speed of sound. So in the numerator, the plus sign applies when the observer moves toward the source. That's the default. In the denominator, The minus sign is the default that applies when the source moves toward the observer. And if either one is not moving, either the observer or the source, then that second term would disappear. Like if the observer is not moving, this term disappears, and you're left with the equation that we already had. So this isn't anything new, but if you like it, it's a more compact way to think about it. So I'll leave that there for you to check out. Another thing to check out, this is an optional video, but this is a favorite, and it highlights the Doppler effect, that it's the apparent change in frequency of a wave caused by relative motion between the source of the wave and the observer. So there you have it. That is the Doppler effect. You can hopefully watch that video. I'll add that to the playlist. And then there's some cool sound applications to the medical field in the very last video. So that is the end of 16.9, the Doppler effect.